Sample means and approximate standard normality. We've looked in previous work and we've investigated, discovered the distribution of the sample means, which is x bar. We've looked at that phenomena around that, and we've discovered and applied the central limit theorem, and that central limit theorem says that provided we have a sample size sufficiently big, which is generally taken as at least 30, we can say that the population's mean equals the sample mean, and the standard deviation of the population is equal to, well, the standard deviation of the sample means is the population standard deviation over the square root of n, where n is the sample size. Now, where we go further from here is by standardization, and you'll recall the little formula for z-scores from your previous work. Essentially, we're using that concept. Okay, so that's what we mean by standardization. Okay, we're doing standardization. Did I spell it right? Standardization, we can say that the distribution of the random variable z, alright, we've seen z-scores before, is a good approximation for the following. Now, if we look at our z-score formula, and we apply it in this context of learning, we would get x bar, capital X bar, minus mu over sigma on root n, okay, which is that sigma on root n there. Okay, and you can see that there's clear links between the z-score formula that we've looked at with our previous work on standardization that you should have experienced well and truly before watching this particular video, and the central limit theorem. Okay, so x minus mu over sigma on the square root of n. So for the purposes of this video, but especially for the next video, which will talk about confidence intervals, we use a lot of the concepts and findings and phenomena that we've experienced in the past with our math methods work on probability and statistics. Okay, so we're going to be using that normality of this expression and performing some calculations around that, okay, through a bit of manipulation. So more about that in the next video. It's nice to know where we're headed, and we'll talk also about the variations in some of the notation here. You might be able to see sigma there, but s there, and you might be able to see x bar there, and mu over here. All right, and we're going to talk all about that, but next video. But this is where we're headed, and the standardization is actually important for some problems that we experience even before we get to confidence intervals as a topic. Okay, so here is one such problem. The heights of a certain population of men can be assumed to be normally distributed. Always look out for that. If the question provides it, make sure you soak that up. Okay, we're given the population mean is 179. The standard deviation for the population is 9. Given that the probability of a sample's mean height being greater than 188 is given as 0.0228. Determine the sample size. So this is a bit different, isn't it? We've got to determine the sample size instead of being given the sample size. Okay, so the idea of these sort of questions is standardization. Okay, so we'll write down a few bits of information consistent with the central limit theorem. Mu will equal the mean of the sample means, the expectation of sample means, and we have 179, and the standard deviation of sample means is the population standard deviation over the square root of n, which is not known. Okay, so what we've been given here is the probability of x bar is greater than 188. We have that much, and we have its value, which makes this a little bit different to some of the things we've worked on before. So, standardization time. So the left-hand side equals the right-hand side, where the right-hand side is z is greater than 188 take 179 over 9 on root n. So I've just applied that there, okay? So then we have a little bit of simplification occurring here. 188 take 179 is conveniently 9. You won't always get numbers as convenient as that. And you'll actually have 9 over 9, which is on top of root n. And so that, if you think about how division by fractions works, the 9's will cancel out and you'll just have square root of n here. Okay, you might need to work that through yourself if you can't see it. But that certainly is right. And that equals 0.0228 given. Now think about our normal distribution, standard normal distribution. And we've got some z-score out here. The probability of something above that, alright, roughly looking at that, probability of a mean above that is 0.0228. Alright, now I want to use inverse normal from our graphics calculator, the process of inverse normal, which is cumulative, which goes from left to right, you might recall, okay? So it goes from minimal to more maximal. So I want to actually, that you'll be able to get the same z-score by using that, but we need to find the complementary probability. Alright, so that should be familiar from our work we've done in math methods. So I won't be going back through all that, so you might need to revisit that if you've forgotten. So to find the complement, we go 1 minus the given probability, as you can see there on your screen, and that will equal probability of z being less than this particular score here, okay, which is, all we know it is root n, and we write less than, okay, less than root n, less than, okay, and that will be 0.9772, okay, is that probability. So the delay there, I thought I had that paused. Just recapping, we're using inverse normal on 0.9772 to find our square root of n value, which will give us our z-score there, our quantile. Alright, so with whatever technology you're using, this is a TI Inspire, we've got probability distributions, inverse normal, and we've got 0.9772. It's a standard curve, so we have our mu as 0 and our sigma as 1. It's standardized, okay? Remember that from your previous work. It's a standard normal distribution, z-scores. Okay, so we get 1.991. And that will equal root n. So n, square both sides, n is 3.996 to 3 decimal places, so we'll need about 4. So let's interpret the question again. For what? we will need 4 people. Okay, so given that the probability of a sample's mean height being greater than 88, determine the sample size under those conditions if the probability was that. Okay. Now we didn't need n to be greater than 30 in this because it was already normally distributed. Okay, so that's fine. If you're worried about n being so little, it's a normal distribution anyway. And from our previous work, we know that's fine. So it's 4. So 4 men would be needed, would be in that for that probability to arise. The next video is on confidence intervals.